All right, welcome to our first of the online lectures. This is the review for exam 2. Scheduled due date for this would be March 30. And first, a review of the course changes due to the switch to online model. Things have changed since we met at the last before spring break. And so I have to have a few changes here compared to what I presented to you then. So PTQs, no change in PTQs. There'll still be one potential test question you'll have to turn in for each lecture where new material is introduced. Today's not new material, so there's no PTQ for today. It'll be due at 11 a.m. Central Daylight Time. So whatever time zone you're in, make sure you adjust for the Central Daylight Time, because Lincoln Time is the time we're supposed to have everything. And your submission will just be on Moodle. So the PTQ assignments will be changed. So when you click on the PTQs, they're not changed yet, but when you click on them, it will have a place for you to type in your question. Lectures will be, as I said, created on the Surface Pro and uploaded to YouTube where you're watching this now, except for I will upload them early. This one I'm uploading only 5 days early instead of a week early, but I will try to have them up there a week early so you have more flexibility in when you watch them. Also, we were told after spring break started that spring break is extended for a week, but we have to finish class the same time as normal. So we have to add those 3 classes into our schedule. We can't skip them. We have to cover everything. And so with that requirement, I'm adding a lecture not every Thursday, not this week, and not the final week. So I'm adding 3 Thursday lectures to make up for the week of lectures that are lost because of the extended spring break. Laboratories, I'll give you either dry lab data, that is, I'll give you data and have you analyze it, or I will have you do a computer simulation. I haven't set up the lab schedule yet. I have made a revised lecture schedule, which you can look at on Moodle and see what the new schedule is for everything. I will be conducting one-on-one oral exams with each student via Zoom. I will ask you to have a mirror with you and a camera so that you can use the mirror to show around. So if you're using like your laptop and using your laptop camera, then you can put the mirror in front and show your full screen and that kind of stuff. And then we will do the exam like that. You will actually have the exam form visible on your computer screen via Zoom, and you can scroll up and down and whatnot to view different parts as you like. And we will talk things through. You will give your answers verbally, and I will be scribing and asking you more questions and that kind of thing. Office hours, of course, you can contact me via email anytime you like, and I will certainly try to answer. But I will also meet at 10 a.m. I did not put here the day of the week, 10 a.m. on Wednesdays. The reason for having these special sessions on Wednesday is because your homework is due on Wednesday. So you can come in with your questions about homework on Wednesdays. There will be no homework due until after exam 2. So we don't have anything pressing there, but we do have preparation for the exam, which is part of the reason why I scheduled the homework sessions for what is actually today, the day I'm recording this, a week before the exam. So you have time to ask me questions there. And then I will send you each Monday an update telling you what's due, what's coming up, and so on. So that's how things should operate. We pray for the best. So here's the periodic table. There's a lot of things you have to be able to do with this periodic table, but you don't have to have it memorized. You will have this exact periodic table in the exam. So you will be able to look at this and you'll need to know, for instance, which ones are the halogens. Well, that's this. The group 17 is the halogens. You'll need to know which ones are the alkali earth metals. Well, that's these ones. Alkali earth. And which ones are the noble gases. That's these ones here. Noble. gases. Which ones are the alkali metals? That's these. And which ones are the transition metals? That's all of these babies. You don't have to know the lanthanide series or actinide series. They're actually labeled there. You don't have to know semiconductors. You don't have to know the halogens. You just have to know that in terms of the areas. You should know that these are organized based on their chemical behavior, that everything that's an alkali metal has a similar chemical behavior. Alkali earth, there are some metals, has similar behavior. Halogens all have similar behavior. And noble gases all have similar behavior. And that's because they have the same valence electron structure. That is, the structure of the electrons in the outer shell is the same for everything in a given group. Further things you should know is relative electronegativities. The electronegativity is highest here at fluorine, lowest down here at francium. So electronegativity is highest electronegativity, high electronegativity, and down here we have low electronegativity. And actually associated with that, the sizes are its biggest on the left and biggest at the bottom. So the biggest atoms are going to be, and I'm not counting the lanthanide actinide series in my evaluations here, the biggest atoms are going to be the francium atoms because they are low on the table and far to the left. The smallest, again, the fluorine. Now, why are the noble gases not considered in either of those? Well, the noble gases, they're noble. They actually are going to be very small. They're probably, the noble gases could be considered in the size evaluation. In electronegativity, the noble gases, electronegativity is how much you want to grab an electron, hold on to your last electron. The noble gases are very happy with their electron situation. They don't want to grab one. They don't want to give up one. They just want to stay where they are. So that's why we eliminate them from our electronegativity calculation. I will, by the way, block out this here that tells you what each of the groups are, because obviously that would kind of make it so you didn't need to know that. You should remember this here is the atomic number Z, and changing pen color just so we can have some contrast. This here is the atomic mass number A. A is a measurement of the mass of a single atom in atomic mass units, or, as we learned, the mass of 1 mole, that's 6.022 times 10 to the 23rd atoms, 1 mole of that element in grams. And you need to know that transition. These numbers up here in the right column, we didn't talk about those with regard to the periodic table because it's not typically something that I've seen in periodic tables, but obviously it exists in some. And this here is telling us it's possible ionization states. If it's a +1, then it is happy to give up 1 electron. Notice hydrogen +1 or -1 is happy to take an extra electron or to give up an electron. Beryllium +2, it's happy to give up 2 electrons, and so on as you go along. Oxygen a -2, it wants to grab 2 electrons. Okay, enough on the periodic table. Reviewing chapter by chapter. Chapter 12, we learned about atoms in the periodic table. So we know you have to know that the nucleus is composed of protons and neutrons. That's the nucleus. Atoms are protons, neutrons, and electrons, but the electrons are in a cloud that is around the nucleus. We don't know exactly where any electron is. We only can talk about where we're most likely to find an electron if we go looking. But we can't say, okay, if it's here, it's going to be there next. That kind of information we just don't have. We don't have the ability to know that. Atomic number, we just talked about that, and the atomic mass number. Electron shells. The shells I did not talk about in the preceding one, but you have two electrons that go in the first shell, and hence the first period has two elements: first electron, second electron. The second period has two electrons in the S shell and 6 electrons in the P shell. So there's a total of 8 electrons in the second shell, and hence 8 elements there. The third line, the third period, also has 8 electrons that go in that shell. And there's a little bit of obfuscation here, but you should be able to just look at this and say, aha, we have in the 1, 2, 3, 4th shell, we have 2 plus 1, 2, 3, 4. It should be 10. You can look at the numbers up here. From 3 to 12 is 10. We should have a total of 18 electrons in that shell. And then likewise here, go down to the cesium. Remember, 57, this lanthanide series should be all where that box is. And so it has even more in that shell. Okay, and yeah, I've already talked about the things you need to know there and reminded you I'm going to block out the key. Also, know what a quantum theory means. A quantum theory means that you're talking about discrete levels. In the case of an atom, you're talking about discrete energy levels that the electron nucleus, we just say the electrons can have, and that results in also discrete, in fact, Bohr's original was discrete angular momentum. That was his only discrete thing when he came up with the quantum model. Now we have energy, angular momentum, and a number of other things. So it's discrete levels instead of continuous. You know, if we talk about a planet orbiting the sun, it can have any energy orbiting the sun. It can have any distance from the sun. It is allowed. And so atoms, we have these discrete energy levels, discrete angular momenta. And that's what makes the quantum model. And so the distinct line spectrum, remember when we wore those cool glasses and we saw only certain colors for the helium, that's because you have the energy levels in the atom, and electrons that are excited to a higher state can fall. So for instance, an electron that's in this state could fall to there, or it could fall to there, or it could fall to there. But there is a different energy for each of those levels. And when it falls, energy can't be created or destroyed. So it gives off light with an energy that's equal to Planck's constant times the frequency. So the bigger the energy drop, the bigger the energy, the bigger the frequency. So this would be a high frequency for the one on the right, a low frequency for the one on the left. So that's why we have the distinct different colors, because frequency corresponds with color. Okay, radioactivity. Remember we did the radioactivity lab with the rolling of the dice. Know what it means for an atom to be radioactive. That a radioactive atom has an unstable nuclear configuration. The way I illustrate that is like you might have an example of protons and neutrons that are lined up on a vertical sequence on your table. So here's your tabletop. There they are. You have proton, neutron in my example. So that would be a radioactive helium nucleus. I'm just using that because it's simple. It's not stable because if something bumps it, it would obviously fall over, right? It's not a stable tower. And so that could become, if you bump it or if something happens to it, it could fall down and give you a new configuration that has something like, and I can label these as seems appropriate, proton, neutron, neutron, proton. This configuration here is much more stable. G difference has to go somewhere, and it comes out, in this case, it would come out as a gamma wave. If this actually occurred, I do not believe this occurs, but it come out as a gamma wave or gamma ray, which is a photon. So it has an energy of HF, and that's one type of radiation. That's the gamma. It's electromagnetic waves, so they're really hard to stop. The other two that we talked about, there's a lot of other types, but these are the only ones that we talked about, the only ones you need to know, is an alpha emission where a helium nucleus comes out of the nucleus. So imagine you have the uranium that has an atomic number of 92. That means it has 92 protons in the nucleus, and it has an atomic mass of 235. That means the number of protons plus neutrons in the nucleus is 235. So we have Z equals 92, A equals 235, and we know that the number of neutrons must be the total things in the nucleus minus the number of protons. And so that would be, that was nice, 143 neutrons. Yeah. So we know it has 143 neutrons and 92 protons based on those numbers. Now, if it undergoes alpha decay, if we have uranium undergoes an alpha decay, the alpha has 2 protons and 2 neutrons, which means 4 nucleons. Then we're going to have something that has 92 minus 2, so 90 total protons. And 235 minus 4 is 231 total nucleons. And that, I believe, is thorium. Now, we can go back and check the periodic table to make sure that I remember it right. So here's uranium. If you lose 2 protons, it becomes thorium. Not too far. So alpha decay is going to transmute the element. That is, it's going to change from one element to another element and give off this alpha particle. Now, if you want to be technical, this alpha is a 2 plus because it has no electrons, and this thorium is a 2 minus because it has 2 extra electrons. But very quickly, the thorium is going to give up its extra electrons, and the alpha is going to collect electrons and become a regular old helium atom. That's how helium gas is produced in our atmosphere. Beta decay is when the nucleus gives up an electron. Now, that's an odd one. How can the nucleus give up an electron? It's a tricky question because the nucleus has no electrons. The nucleus has only protons and neutrons. So what happens in a beta decay is effectively a neutron decays to produce a proton plus an electron. Zero protons, 1 neutron, a neutron, 1 proton plus neutron in a proton. The electron, of course, has no protons and no neutrons. We actually often will put a -1 there because it then makes the numbers of protons conserved. So this here is my beta particle that comes flying out of the nucleus. So the number of protons increases by 1 when you have this beta decay. Half-life is statistical. That's why we rolled dice for it. And it's the time during which 1/2 of all of your radioactive nuclei will have decayed. So, for instance, for carbon-14, that half-life is around 5,730 years. So if you have a sample that has 10 grams of carbon-14 in it, and you wait 5,730 years, you're only going to have 5 grams of carbon-14 remaining. What happened to the rest of it? Well, it will have decayed into nitrogen. I believe it's into nitrogen. I didn't look it up. Nuclear fusion and fission. Fusion is when two things merge. So if I have a proton that hits a helium, well, let's do a proton, which I'm going to write here as a hydrogen 1, and it meets a deuterium, a hydrogen 2, that can produce a helium 3. That's what we would call fusion. Fusion releases a lot of energy if you have small things building up to something bigger. What's small to bigger? This stops at iron. Iron is the most stable nucleus, iron and nickel. And so you can fuse things smaller than iron to produce iron and release energy. You can't fuse things larger than iron and release energy. It takes energy. It's exothermic if it gives up energy. It's endothermic if it absorbs energy, requires energy. So fusion stops at iron because it absorbs energy. The only way that we have elements bigger than iron is when we force fusion by putting a lot of energy in. That happens in star collapse, as we'll learn in our astronomy section. Now, fission is the opposite of fusion. Fission is when you take a large nucleus and you split it into small nuclei. So the example I showed, well, that's not fission. A uranium 235 will split into two smaller elements, and I think potassium and barium is the one we usually show, plus 3 neutrons. But they're weird isotopes of potassium and barium, very radioactive elements. But it's a big thing that breaks into smaller things and releases energy. Once again, this is going to have to be something bigger than iron, and it's going to break up into something closer to iron. You'll notice the fusion example I gave you, it doesn't have a radioactive element that is produced. The uranium does have a radioactive element, 2 radioactive elements in this case, that are produced. So the uranium has a lot of radioactive waste problems. That's fission has radioactive waste problems. Fusion generally doesn't. So why do we have fusion or fission power plants but not fusion power plants? Well, fission power plants we can do because we can control those. Fusion power plants, we don't have a way to control it. The sun, in fact, is a fusion power plant, and it's controlled by gravity, but we don't have a good means yet of controlling it. But it's a holy grail. It's something that scientists are working hard at to try to figure out how we can harness that fusion power, because if we do, then our energy resources shift from oil, essentially, to water. There's a lot of hydrogen, deuterium, tritium in water, and that makes a good fuel for fusion. So our fuels shift, and we have a very plentiful supply of water. We'd have a very plentiful fusion supply to last many generations beyond us. Chapter 14, make sure that you can define the difference in a chemical. A chemical is anything that's made of atoms. So, for instance, water, vitamin C, phenolphthalein, those are all chemicals. A molecule is a grouping of atoms into one basic unit. So an example would be something like sodium chloride, or let's say methane. Those are examples of molecules. Methane, you have a gas of methane, you have a whole bunch of CH4s that are flying around. Element means I have a substance made of one type of atom. An example might be gold, G-O, or ecium. One type of atom if you have pure gold. A compound is when you have a substance that's made of more than one kind of atom. For instance, if I have a block of salt, that's a compound. I should put table salt because, as you learn, table salt is not the only salt. You have a whole bunch of NaCl's, but you only have one molecule in your substance. A mixture is when you have more than one type of molecule in your substance. So a mixture might be salt water, which is H2O plus NaCl. And as we learned, that becomes H2O plus Na plus Cl minus, which does some other things. An alloy is a mixture of metals. So you might have white gold, which is gold and some platinum that are mixed together. Physical properties, those are changes that we can see. Things like color, how hard it is. That's physical properties. So water, if you freeze water, it's a change in physical properties. It's still water, it's still H2O molecules. So you didn't change the molecules, you just changed what it looks like and what it feels like. Chemical properties, it has to do with when you actually change the bonds. So a change in chemical properties almost always results in a change in physical properties, but you can have changes in physical properties without a change in chemical properties. Then our simple compound naming, remember you take the element on the right, or left, excuse me, on the left of periodic table. Periodic table first. Add "-ide" to last element and use prefixes to disambiguate. So for instance, we have H2O as an option or H2O2 as an option. So using the simple naming method, H2O would be dihydrogen monoxide, 2 hydrogens, 1 oxygen. H2O2 would be dihydrogen dioxide. Common names, water and hydrogen peroxide. But the common names you're not being held to. It's just being able to do these simple naming things. Chapter 15, how atoms bond. So we have the electron dot structure. The electron dot structure is easy. You look at, let's say, carbon. Carbon is, if you look at it on the periodic table, it's the element with 6, has a mass of 12.00. And so it has 6 valence electrons because it has the same number of valence of electrons as it has protons. And then you just take, for the shell, you're like, how many of those are in the first 2 columns and the last 6 columns? The valence electrons are only going to be the first 2 columns and the last 6 columns. And so with carbon, all of those are valence electrons. And so you just take carbon and you start and go 1. Let me change colors for the electrons. Just go around in a circle doing 1 at a time at 90-degree angles. Wait. Yeah. Carbon has 4 valence electrons. It's 6. It is 6 there, but it has 4 valence electrons because I can't remember things. Remember, the periodic table has hydrogen, helium, and then you have, I think it's beryllium. Is it neon? No, I don't think it's neon, actually. What's under helium? I'm not going to go back and look. Obviously, I haven't memorized this like I should. I mean, this could be magnesium here. Okay, I am going to go back and look. There it is. So it was beryllium, boron, carbon, nitrogen, oxygen. It was neon as well. So actually, let's just look here. So these two were valence electrons for the first one. And then we have 1, 2, 3, 4 for carbon. That was my finger, and it's not supposed to mark. So it has 6 protons, but it has 4 valence electrons. So I put the 4 valence electrons on there. Each lone electron can form a covalent bond. So carbon can form 4 covalent bonds. If we were to do nitrogen, nitrogen has 5 valence electrons, right? 1, 2, 3, 4, 5, 6, 7. And so the nitrogen, it would be 1, 2, 3, 4, 5. Now it has a lone pair and 3 available bonds. On the other side of that coin, if I had done boron, boron has just 3 valence electrons. So it can form 3 bonds just like the nitrogen, but it doesn't have the lone pair. So in your last homework assignment, you were asked about why a compound that has nitrogen is a polar molecule with nitrogen and 3, I think it was hydrogens. So why is NH3 a polar molecule, whereas BF3 is non-polar? And the reason is the nitrogen is going to have this lone pair sticking out on one side. So it's actually going to look like, these 3 things coming down with the lone pair of electrons here. So this side is negative and this side is positive. Whereas BF3 is going to be symmetrically distributed. Each one of these is going to be negative, and that's positive in the center, but it's symmetrical, so it's non-polar. Okay, so that's the electron dot structure. Valence electrons are the electrons in the outer shell, the ones that are available for bonding in covalent bonds. And we just talked about how we can identify them. Different types of bonds. Ionic bonds, that is electron passes from one atom to another. So they both become ions, and then they're held together because opposites attract. Covalent is not an electron passing from one to another. It's electrons shared between the atoms. So each atom essentially keeps its electron, but it's sharing. So I have ice cream, you have ice cream. If I take your ice cream, I have 2 and you have none, then you want my ice cream and you hang around me because you want my ice cream. That would be ionic. Covalent is I have an ice cream and you don't have an ice cream, and we share my ice cream and we're happy because we're sharing it. The next ones, the green ones here, are not bonds that hold atoms into molecules. They're bonds that hold molecules to other molecules. So these are between molecules. The top ones there were between atoms to make a molecule. My color coding is ridiculous. And so these are listed in order of strength for the ones between molecules. Ion dipole, that is like you have a sodium atom that's going to naturally give up an electron, become a positive ion. And you have a water molecule. That water molecule has a negative side and a positive side, or we might use ammonia. The ammonia molecule has a negative side here. And so the sodium ion says, that negative looks mighty fine. And so it bonds to the ammonia. So that's ion dipole. That's the strongest of our bonds that aren't molecular bonds. Dipole would be like having these 2 ammonias. Well, it's water. Water is a great example of dipole. Water The oxygen is much more electronegative than the hydrogens. And so the oxygen has a net minus. It pulls extra electrons, so it's a net minus 0.7 charge, whereas each hydrogen is a net plus 0.35 charge. Because the hydrogens don't get as much of their electron in the share. It's not a uniform share. And so another water molecule comes by and its oxygen says, ooh, look at that hydrogen. And it bonds to that hydrogen. And so that is a dipole-dipole bond. And we call it a hydrogen bond in this case where it involves the hydrogen. And it's a very strong bond in terms of holding molecules together, which is why water has that very unique situation with ice that when you freeze it, it actually expands rather than contracts like almost everything else does. And water has a much higher melting and boiling temperature than it normally would have because of that strong dipole-dipole bond, hydrogen bond. Dipole-induced dipole is when, for instance, you have a water molecule that is a natural dipole, and then you have something like, let's say, hydrogen molecule. Hydrogen molecule is two H's bonded together. Well, the hydrogen molecule is symmetrical, perfectly symmetrical, because the electronegativities of the H's are identical. But if it comes close to the water molecule, the negative of the water molecule of the oxygen, stop doing that. The negative of the oxygen is going to force negative charge away, making the hydrogen closer to a positive, the hydrogen farther negative. So that's an induced dipole. And then you have a bond between the dipole of the water and the induced dipole that it's made. Induced dipole is the very weakest. That's when you have something like hydrogen molecules, and hydrogen molecules bring them close to each other because the electron cloud, one of them pushes electrons away from the other, and then you have an induced dipole that induces a dipole back, and they have a very, very weak bond. Metallic bonds are completely different. Metallic bonds, you are just sharing electrons along the entire metal. So you put in something else that shares, and the metal just kind of shrugs and says, sure, you're one of us. And so that's how you make alloys, is because they have a completely different type of bond. Now, a polar bond occurs when one atom is more electronegative than the other. So in these examples that I showed here, those were polar bonds because the fluorine was more electronegative than boron. The nitrogen was more electronegative than the hydrogens. So those made polar bonds. But this one was, because of its symmetry, not a polar molecule. The other one was. The stronger or the bigger the difference in electronegativities, the more polar it is. So in fact, we set up some rules about ionic. I'm going to change. Oh, that works fine here. If we have the difference in electronegativity, delta electronegativity, and you do need to know these numbers. If it's greater than 2, don't worry about the units, just greater than 2, then it's going to be what we call an ionic bond. If it's between 1.6 to 0.5, then we'll call it a polar covalent. And if it is less than 0.5, then it's just a regular old nonpolar covalent. So you can determine if it's polar or not based on electronegativities. All right, chapter 16, mixtures. I've actually already talked about a lot of this, but make sure you can identify the difference between elements, compounds, homogeneous mixtures, and heterogeneous mixtures. There was a lot of difficulty on this homework problem, so make sure you review the homework. It's already been handed back, and that you can identify the difference between a compound, a homogeneous mixture, and a heterogeneous mixture. Solutions, know how to calculate the molarity. The molarity is the number of moles of solute, the thing that is dissolved, divided by the number of liters, that is volume, of not solvent, but solution. So what do these words mean? Solute is the thing that is dissolved. Solvent is what it's dissolved in, and solution is the sum of those two. A saturated solution is when you have dissolved as much as you can. So in our lab where we had the unknown powders, you dissolved it, and you always had some that didn't dissolve. Well, you almost always had some that didn't dissolve. And so that meant you were in a saturated situation where it had as much dissolved as it could hold, and so the rest didn't dissolve. Unsaturated, if it completely dissolved, then you probably were unsaturated. You probably could have dissolved a little more. A mole is (6.022) times 10 to the 23rd molecules. That's Avogadro's number. You don't have to have it memorized. It will be on your equation sheet. So 6.022 times 10 to the 23rd molecules is a mole. And 1 mole has a mass in grams equal to the molecular mass in atomic mass units. U is the symbol for atomic mass units. So for instance, you had a problem where you're supposed to compare H2 to H2O if you had 2 moles of each. Was it 2 moles of each? Yeah, it was 2 moles. So 2 moles of H2. H2 has a molecular mass of 2 atomic mass units. And so if I multiply that by 2 moles, that's equal to 2 times 2 is 4, and we change a mole times atomic mass units grams. Whereas the water, H is 1, O is 16, so 2 times 1 plus 16 is 18. I'm going to have 2 moles times 18 atomic mass units. 2 times 18 is 36 grams. And so obviously 36 grams is bigger than 4 grams. We didn't talk about soaps and detergents, so moving on. Chapter 17, how chemicals react. Be able to balance a chemical equation. Remember a reaction. You need to have the same number of each atom, type on each side. So if I have H plus O yields H2O, and that's H2 and O2. If I add heat, it'll form H2O. That's not balanced. If you look at this, there are 2 hydrogens, 2 oxygens. On the other side, there's 2 hydrogens and 1 oxygen. I should use some color coding. Two and 1, I did that backward. So the blues, the oxygens don't match. So to make that match, I'm going to have to make it 2 H2Os, which makes this a 2 and makes that a, I don't know what color I chose, a 4. Now the O2s match, but the H's don't. But if I make 2 of this, then I have 4, and now it's balanced. So you need to be able to do that. And I showed you a way in class. You can do it a number of different ways. Know how to convert from atomic mass units to grams. Well, we just did that example. Right here where we multiplied by a mole, in this case 2 moles. So we had 2 times 2 is 4. A mole times atomic mass unit is a gram. Understand how temperature, concentration, and catalysts affect the reaction rate. Temperature, you have more energetic collisions and more frequent collisions because they're moving faster. Concentration, if you have a higher concentration, you're going to have more frequent collisions because they're closer together. Catalyst is a whole different ball of wax. The catalyst lowers the energy necessary to start the reaction. We call that the activation energy. So catalysts lower the activation energy, to lower the energy you need to make a reaction occur. The reaction will be exothermic if it's giving off energy. And if it's giving off energy, it moves to stronger bonds or a higher bond energy, because the bond energy is how much energy it's going to take to break it apart. So if you add up the bond energies of the things that were put in, the reactants, and you add up the bond energies of the product, the things that were made, if the bond energies of the product is bigger, then it's held together more strongly, and it is exothermic. It's going to give up energy equal to the difference in those. If the product has a lower bond energy, then it's endothermic. You had to put in excess energy to make that occur. Chapter 18, acids and bases. We had to memorize bad bases. Except, I think that was the word we used. Not said protons. Acids donate protons. So an acid is something that's going to give up a proton. That's a hydrogen ion. It's a proton because a hydrogen atom has an electron, a hydrogen ion doesn't. A base accepts that. So you should be able to look at a chemical reaction and say, aha, this water gave up a proton to become OH. So that water, since it donated, it must have been an acid. Or in another case, you could have a water accepted a proton to become hydronium, in which case it would have been a base. Water can be both an acid and a base. And so acids and bases, you need to be able to identify them based on this. And identify salts are the precipitates. So if I take, for instance, a hydrochloric acid plus a sodium hydroxide base, the hydrochloric acid is going to donate an H, and so I'm going to have chlorine by itself. The sodium hydroxide is going to take on an H, but then that OH2, that's water. And so what I end up with is Na plus Cl plus H2O. And then the sodium and chlorine, if I have a saturated solution, they will precipitate out, giving me a solid salt. Now pH is minus the log base 10 of the concentration of hydrogen protons. So the concentration of hydrogen ions in water, if I have water, I'm going to have the concentration of H plus is equal to the concentration of OH minus is 10 to the minus 7. So water is going to have, we focus on this one, 10 to the minus 7, log base 10, 10 to the minus 7 is minus 7, because log base 10 means what exponent would I have to raise 10 to get that value? Well, clearly, to get 10 to the minus 7, I have to raise 10 to the minus 7. So minus a minus 7, and it's 7 for the pH of water. If it has a higher concentration of H plus, then it's going to be like 10 to the minus 4, right? That 10 to the minus 4 is a bigger number than 10 to the minus 7. And so if I put 10 to the minus 4 here, log base 10 of 10 to the minus 4 is minus 4, minus negative 4 is 4. So a pH of 4 has a higher concentration of H plus and is more acidic. So things with a pH that is a Smaller number than 7 are acids. Things with a pH that is a bigger number than 7 are bases. We actually didn't talk about acid rain. And I believe that takes us to the end. I will have the vocabulary sheet updated shortly so you can review that for vocabulary words. I have everything graded and returned to you that has been turned in. So you have everything you need to prepare for the exam. I will be available, well, it is today actually, at 10 a.m. to answer your questions. All right, I'll talk to you later. Bye.